Let's now look at problem number 2 on exam number 2 from ECE 207, summer of 2007. This particular problem is really wanting us to examine a circuit under two different extreme cases, or two limiting cases, not so much extreme, but we want to look at two conditions that this circuit can be in, or two configurations. One for time less than 0 when it's already reached steady state or when it's in steady state. We'll throw the switch at t equals 0, and then we'll wait until the transients die out, and we'll look at what happens with these particular variables as t gets large or in steady state condition. So we have two different circuits, and they're both going to be coming about when we look at the switch when it's in one of two states, and those states are changed, or the state is changed at t equals 0. If we look at this particular circuit, this switch is initially closed for t much less than 0, and this particular circuit or switch is opened before t equals 0. What we want to realize, and so this we might call t negative in terms of the time that we're wanting to look at this particular steady state behavior, and we can also think that when we're looking at maybe the capacitor voltage, we can measure a voltage across an air gap, and that may be useful in finding the voltage dropped across a capacitor after it's reached steady state condition. In this particular circuit, this 2 amp is just going to flow there, and effectively this point or location is connected to the bottom node. And if we redraw this particular circuit, the inductors in a DC steady state condition, Eli says that V sub L is equal to L di dt. With constant sources applied to this circuit, then this particular current is going to be constant. Its time rate of change is going to be 0. So the inductor voltages are always going to be 0, and that means in DC steady state condition, these become, if the voltage dropped across those inductors becomes 0, those effectively become a wire. If we look at ice, which says that I is equal to C dV dt, again, voltages and currents after these have reached steady state or in a steady state condition, this voltage is going to be constant. Its time rate of change is 0, and consequently we have 0 current flowing through that capacitor, and effectively we can get rid of that, and we just have that particular capacitor removed or opened up in terms of a circuit element in its steady state condition. Under those conditions, with these switches in the fashion that they are in for t less than 0, let's redraw the circuit, and we now have this 3 ohm resistor shorted to ground. The original 3 ohm with the inductor now replaced with the short circuit. The capacitor gets opened up, and we have this resistor which has no current flowing through it because there's no path for that current to flow through. Consequently, since there's no current through this 3 ohm resistor, there is no voltage drop across it. Here's another 3 ohm resistor. The inductor shorts out, and the only thing remaining is this 5 volt voltage source that we have on the rightmost side of our circuit diagram. We can now identify the variables of interest. We want I sub L sub 1's current. We would like to know what this voltage is across this capacitor, and we also have I sub L sub 2 that we want to determine. These are all going to be constant values for t negative because we've been in this condition from minus infinity up to time t equals 0, and we want to know what's it doing for t much less than 0, and it's now in this steady state condition prior to t equals 0. If that's the case, then there's several ways that we can analyze this, but if we look at this being, let's say, one node, then we simply have that one node voltage to find in order to solve this particular equation. If we write KCL at 1, in this particular case, we have this current going to the left. And let's call this voltage V1, and since it's in a constant DC excitation circuit, let's call it capital V sub 1. We have V1 over 3, that's this current. Then we have plus this current down here, which is I sub L sub 1. Let's say that's V1 over 3. This current doesn't exist because that's an open circuit, and we then have this current going to the right out of V1, and that's V1 minus 5 over R sub 4, which again is 3, and that's equal to 0. All of those V1s now can be combined, and we can push the forcing term to the right-hand side, and luckily we've selected these resistor values to be fairly convenient. That says that V1 is 5/3 volts. If we need to know now what these different currents are, we have I sub L sub 1 at, let's say, t negative. That was just V1 over 3, or that's now 5/9 for a current I sub L sub 1. I sub L sub 2, I believe we had that colored in red for negative time, is now V sub 1 minus 5 over 3, and we then have 5/3 minus 5 over 3. This minus 5, when we put it over a 3, is going to be minus 15, and so we now have minus 10 over 3 divided by 3, or minus 10/9. For I sub L sub 2, and finally we need to find this voltage dropped across this capacitor, and we could write a KVL equation around that particular mesh or loop and just realize that we can sum voltages across an air gap where this is the air gap that we have of interest, meaning we now have this drop from here to there. Since there's no current flowing through that resistor because of the open circuit, we have 0. Then we have minus V sub C. Now we're doing our KVL equation. We have minus V sub C plus R sub 4, which was 3, times I sub L sub 2 at t negative, plus 5 is equal to 0. And I sub L sub 2 of t negative was minus 10 over 9, or V sub C is now equal to 5 minus 10 over 3, or we now have 15 over 3 minus 10 over 3, or 5/3 volts for V sub C in that condition for t less than 0. For positive values of time, we now have this particular switch open, and we have this switch closed, which now allows that to remain open, this one to go closed. Effectively, now we've shorted out that particular source. Remember, we have this DC current source applied for a long length of time for t much greater than 0, or let's say t positive. In that case, the inductors and capacitors have reached their steady state behavior. These inductors become wires again because their voltage drop is 0. The capacitor again opens up because it's now in a DC steady state condition. And let's now redraw that particular circuit under the condition for t positive. We have again this current I sub L sub 1. We have this current I sub L sub 2. And we have V sub C. Those are still associated with the same elements, but now we have a different circuit because of the switches being in different positions, and this was now 2 amps. But even though this is a different configuration, we still have this particular node, node 1, that we can write our equations with respect to. In this case, though, I might say that I have this particular current going into the node. I have I sub L sub 1 coming out and I sub L sub 2 also coming out, meaning if I now write KCL at node 1, I can say that 2 is equal to I sub L sub 1, this is for t positive, plus I sub L sub 2 at t positive. And I simply need to rewrite those in terms of V sub 1. This is now, well, let's call it V sub 2 just to make it unique from the previous problem, but it's a constant voltage now. That V sub 2 is with respect to the top node, node 1, and this reference node down below. We have 2 amps coming in from the left. We have V sub 2 over 3 as our current going down, and going to the right we also have V sub 2 over 3, and that now is our governing equation that allows us to conclude that we have 2/3 V sub 2 equaling 2, or if we cancel the 2 and multiply both sides by 3, we see that V sub 2 is now 3 volts. With V sub 2 equal to 3 volts, we can now see that I sub L sub 1 for t positive is V sub 2 over 3, or 1 amp. I sub L sub 2 for t positive is also V sub 2 over 3, or 1 amp. And finally, V sub C for t positive, we can again use this voltage across an air gap and with that particular concept we can now write KVL around this particular mesh. Again, from here to here, the voltage drop, because there's no current flowing in that branch, is 0. We have minus V sub C plus the drop of this horizontal resistor on the right hand side, which we know to be I sub L sub 2, times that particular resistor value. So we now have minus V sub C for positive values of time plus 3 times I sub L sub 2 for t positive. That's equal to 0, or V sub C of t positive is simply 3 times an I sub L sub 2 was 1, and consequently V sub C of t positive is 3 volts.